My name is Noah. This is my Physics 2 Lab 3. You already know what it is, so let's get right into it. In this lab, we experimentally measured the field of a permanent magnet at different points and then used that to calculate the dipole moment and also calculate the magnetic field of that same permanent magnet using a computational model at different points and compared the computational model with the experimental information. And the main tool that we used for this was the magnetic field of a permanent dipole magnet, which was provided in the lab. And this is the formula for that here. In this case, this is a constant. R cubed is the distance from the permanent magnet. And mu is the dipole moment of the permanent magnet. And so this was the formula that underlied our computational model and also how we calculated the dipole moment from experimental information. And so essentially to do the experiment, we slid the magnetometer in a phone around a magnet to measure the magnetic field both in direction and magnitude at different points. And it was important in this experiment that we aligned the ruler with the magnetic field of the Earth so we got less interference with the Earth's magnetic field interfering with us measuring the magnetic field of the bar magnet, but we still did have to do some adjustments, and this was likely the biggest source of error between our actual measurements and the ground truth, was just misalignment with that magnet. But the data we got was still fairly strong, and once corrected for, we calculated a dipole moment of negative 3.16 ampere meters, and we found the magnetic field obviously increased in magnitude with proximity to the dipole, but didn't fall off to zero with distance because the Earth's magnetic field was always present. And in this case, the surroundings, since I forgot to do this, the surroundings in this case would be essentially everything except the magnetometer, and the system would be the magnetometer measuring that at some point. And the initial conditions don't really make sense to talk about in this experiment, so since we're just measuring the unchanging field of a permanent dipole magnet. Now, computationally, the code was very straightforward. It just involved bringing this formula and calculating it based off the dipole moment we found experimentally, and various different r vectors depending on where we were in space. And this computational model was actually fairly successful. For example, for one of our readouts, this specific orange arrow here, we calculated the magnetic field at that point to be 10 to the negative 4 Tesla, when we actually measured it to be 1.23 times 10 to the negative 4 Tesla. So very close, on the same order of magnitude, showing the computational model is effectively predicting where the magnetic field will be at different points. As for the what if we hadn't aligned the permanent dipole magnet with the magnetic field of the Earth, if we hadn't taken that step to make sure it lines up east to west, then we would have gotten a lot more interference with the Earth's magnetic field and would have had to correct for that in math afterward by subtracting that magnetic field at various different points to isolate the magnetic field of the permanent magnet. And for the second what if question, if an equal magnet were added to the magnet we were using, then the magnetic field that we observed would be doubled, because the formula for the magnetic dipole of a permanent dipole magnet is related linearly to the volume of that magnet. So if we doubled the volume, then the dipole moment would also double. So we would see a doubling in the magnetic field at every point in the same direction. Thank you.